So this slide is pulling together a couple things from a couple of the earlier USGS horizontal accuracy slides, and I've actually included this on your um, data management protocol that you use for the practical exercises in the class. This is something that I think is important enough to include there. It's something that all GIS folks should be somewhat aware of, and applying the national map standards for the U.S. to different scale maps. What this slide is showing us is, um, given those accuracy standards, if we were looking at needing to know in meters, what is the allowable accuracy or the expected error rate that we might find in data sets generated at a particular scale. That's what we're trying to get across here. So under the U.S. standards, if the scale is larger than 1 to 20,000, you can use the calculation here of 1/30th, so 0.033333 rep of 10 times the scale number times 2.54 centimeters per inch divided by 100 centimeters per meter will tell you how much allowable error there is in meters. If the scale is smaller than 1 to 20,000, then you use a slightly different multiplier, 1/50th or 0.02 times scale times 2.54 times 100 to get ground meters. Okay, and below, a couple of examples for 1 to 100,000 scale maps. That error rate, the expected error that we might find, the allowable error for 90% of the sample locations that we might take on a map, they should be within 166 feet horizontally of where they are in the real world. And for 1 to 24,000 maps, to repeat it again, should be within 40 feet of those locations. Or to use the more scientific measurements, for the 1 to 100,000 map, 50 meters. For the 1 to 24,000 map, 12 meters is the allowable error. And so if you receive a data set and you're not sure um, positionally if it's accurate or not, if it's to the national standards or not, meaning federal government standards or not, you can use these equations or the handy little table that I've produced over here on the right to show you um, different scales and the allowable or expected error in them, measured in feet or meters. And again, this whole slide is reproduced as an appendix to the data management protocol. So when you receive a data set, if all they tell you is it's generated at a scale of 1 to 100,000, and you have no other indication about error within that particular data set, the one thing that you should be able to presume about that data set is that all locations should be within 50 meters of where they are in the real world, or 166 feet. Um, and so I keep this handy for the future in case you ever run into a situation where you're combining data sets from different locations, different sources, um, different people or organizations that may have produced them. And if you have no other measure of error in that data set, the minimum thing that that you can say about it, that you should be able to say about it, and that they should be able to defend, is that at that scale, your positional accuracy should be within, these margins that you can see here, or that you can calculate for any given map scale. Another type of error that we must be aware of and that we produce when we're working with geospatial data is topological error. And topology, the root word there, the study of geometric properties and spatial relations unaffected by the continuous change of shape and size of features. In terms that make sense, what we're looking at here is in GIS, how well do the points, lines, and polygons in a vector data set, for example, share their adjacent geometry? How well, in turn, do they then match up with objects and relationships in space on the Earth's surface? And so let's take a look at some examples of those to make it a little bit clearer. So here's a very small set of the variety of topological errors that can exist in a vector data set. Vector data you can digitize as a GIS professional. Just about anything out there on the land surface that you can imagine, that you can see, that you can observe, you can use the vector data model to create points, lines, and polygons to describe it. The examples here might be for area and for a road network. So going across, or looking at, excuse me, the left hand 2/3 of the diagram where we're looking at the line features. Imagine that this is a road network. And so here are some errors that can happen related to two roads that may intersect. Position A shows what we call an overshoot, where the digitized intersection winds up being a cul-de-sac. And where there is no cul-de-sac in reality, there's supposed to be an intersection, but whoever digitized it shot too far. So we're overshooting that line, went way too far, and then they ended it where it was not supposed to end. In position B, we see a line undershoot. Same sort of things happening. Someone's creating a road network. They're digitizing point locations, describing the lines and the intersections, and they missed the intersection, and they created the end of a road where they should have connected together. So that's something that you can manually go in and edit the work that someone else has done or your own work and make those things match up just by extending the line, and you get to position D, the corrected overshoot that has a correct intersection. That means it has the correct topology where the road that's moving from, let's say, the lower right to the upper left matches the direction of the road in reality, and the one that's coming out from the lower left that forms an intersection, that one matches well where the road position is in reality, and the intersection matches where it is in reality. That's kind of what topology is. How well does the vector data set match the locations and spatial relationships that exist on the land surface? Okay, we'll jump over to the right third and look at the polygon. So if we're describing or trying to describe an area by using the vector data set, in this case, let's imagine that this might be the shoreline of a pond. Okay, and so we have a starting point and an end point, and they didn't match, they didn't connect like they should. You know, a pond that doesn't have an outlet, doesn't have a stream flowing out of it, should be one semicircular or whatever shape it is, one continuous polygon for that pond. And so someone started the pond. They did a pretty good job describing it around the edges, the shoreline, and they missed the last point, and they didn't match up quite right. They didn't close the polygon correctly. So what you can do, again, you just extend, you add another line segment to that polygon to close it. Okay, so the part of the diagram I've ignored so far, position E, is showing a corrected undershoot and a little piece of a diagram called fuzzy tolerance. So fuzzy tolerance is something, it's a property that we can use during the digitization process to end polygons correctly, to cause intersections to occur properly by saying, if I am digitizing lines and I have 2-point locations that are within this distance, make them snap together and form that intersection in terms of roads, or close the polygon in terms of the polygon coverage not having the two endpoints meet each other. The fuzzy tolerance setting, or what's also known as snap distance in GIS, when you're digitizing features, that's what it'll do. It'll grab those things and say, well, you told me, you told the computer program that if there's a dangling little point out here in space, it's close to a line, I'm going to make that thing snap across and join that. Okay, so it's something, it's very useful when you're digitizing because it can reduce a number of errors that can creep in, and just eliminate them. So you know that, well, I can get pretty close to this road. If I get within a snap distance, it's going to shoot it across and make that connection for me and end that line properly. Or it's going to close the polygons around the 100 ponds that I need to digitize around. And I can be a little bit sloppy and still wind up with a polygon that does a pretty good job of describing the shape of that feature. You also want to be a little bit careful because sometimes if you set that snap distance too large, maybe you do need to have a cul-de-sac. Maybe you do need to have an undershoot to describe how those roads actually work together. So if when you're digitizing, and you're using a fuzzy tolerance setting, you need to make sure that you're making that setting as small as possible to fit your particular needs, so that if you do have to have a cul-de-sac, your fuzzy tolerance just doesn't automatically get rid of it for you. You want to make sure that that's preserved in your data set. Okay, so anyway, when you start digitizing, this will make a little bit more sense. That comes a little bit later in the semester. So here we're seeing an example of digitizing two areas, maybe two different people working on digitizing the same area, and we're trying to combine their work, or the same person on different days goes through and creates polygon number one with one type of land cover, polygon number two with another type of land cover, and they really didn't do a good job of catching the boundary between those two different land cover types. Well, you can apply a fuzzy tolerance setting to that work and then get rid of all the sliver polygons that don't mean anything. In this case, that these are digitizing errors that were introduced by the human that was doing the work, and they don't have a bearing on anything in reality. They don't exist out there in reality. So we want to get rid of them. So we can apply a fuzzy tolerance setting and a filter to the data set and erase those things, produce that one at the bottom single clean line between the two, and wind up with at least a cleaned up data set, and ideally something that's fairly accurate and topologically correct. If you were doing this kind of work yourself and you discovered that you had introduced this amount of error in the data set, you might want to go back and just do it again, and make sure that you did a good first pass, rather than doing a cleanup operation like this. Sometimes we don't have any choice. We wind up with a data set that is filled with these sliver polygons and other artifacts from different geoprocessing techniques and simply digitizing, and we just need to clean them up and then live with it. But if you're producing the data yourself, you should be diligent and careful and produce as accurate a vector tracing of whatever's out on the landscape at the time you're doing it. Do a good job first, and then you don't have to worry about cleaning up the mess later. And digitizing is something it's fairly easy to do. So it's easy to actually do it well the first time. If you're just being lazy, you're going to pay for it later. You're going to wind up with data sets that are a mess, and then you're going to need to clean up before you use them for analysis or hand them over to someone else to use in analysis. Temporal refers to time, and so temporal accuracy is how up to date your spatial and attribute data are for any given data set. If we use USGS quad maps again, sometimes decades have gone between updates between the different maps. And so you may be working on a current project, and the most recent map you have maybe 15 years between the time it was published and the time you're using it for whatever kind of an analysis you're running. That may be adequate. It may be the only thing that you have as a reference to what the land cover types are, or the spatial locations of buildings, rivers, lakes, natural features, things like that. And that may be too long, too. That 15-year gap may be too much. You might decide I need to find more recent information than that. Printed maps, in particular, are prone to being, by definition, out of date. As soon as you print it, pretty much, you're out of date. Something probably changed on the Earth's surface somewhere within that study area. And as time goes on, more and more changes accumulate, and the map just falls out of accuracy. Modern data sets, and some of the raster data sets in particular, get updated daily on the internet. And so if you're looking for the most accurate and precise data, you're going to try to find the most recently produced data sets. One of the examples that I can throw out there is SRTM 30 Plus, the Shuttle Radar Topography mission, which was produced globally as a digital elevation model for the land surfaces. And SRTM 30 Plus includes marine readings, so it's not just the land, it's also the bathymetry. Okay, on land it's elevation above mean sea level, and if we're considering oceans and bays, it's elevation below mean sea level, or bathymetry. And so that data set is one that's maintained, and it's available on the internet, and it's maintained by incorporating all of the published sonar soundings, and multi-beam sonar soundings in particular, that are conducted by anyone in the world, as long as it was done well and is accurate and fairly recent. They incorporated those readings into the data set and update them fairly regularly. The same thing applies to other data sets that are out there, especially elevation-wise, as the land surface changes during natural events, erosion, flooding, earthquakes, and things like that. Some of the data sets that are available worldwide are more accurate than your printed maps would be even 20 years ago. So anyway, the whole idea behind this slide is you need to be aware of when your data was produced, and is it sufficient for your purpose, or do you need to find something that was produced more recently, closer in time to when you're working. So this slide is kind of an example of one of the techniques that we might use to visualize error, and in this case it's looking at point data. And let's pretend, suppose that the point locations are the dots on a map that we receive from someone else, or a data set that we receive from someone else. But when we compare it to data that we already have, that we know to be accurate, we discover that on this map, look at the arrows, and the arrows are indicating that's where things are supposed to be, and that's the direction that they're supposed to be, away from the points that they're in this particular map. So we're seeing kind of a measurement of magnitude of error being distance and also direction away from where we know it's supposed to be. So if you receive something like this, and imagine that maybe you're comparing, using an example that we've had before, city locations, but this time suburbs around Seattle. And if someone gave you a data set that was full of information about the different city centers, and the city centers were off by this many, consider it in the numbers meaning miles, off by 15 miles in that direction from where it's supposed to be, or off by 12 miles in that direction from where it's supposed to be, or 17 or 2 or 1. Okay, but you have all of this accumulated error in there, and you can visually see it because you're superimposing two data sets on top of each other. Okay, if you have that much error and you can detect it visually, you can see it, you should really be wondering about that data set, and if and would it be appropriate to use in this case? No, you just throw it out. It's not produced well. It was not done with the rigor that we need in scientific work. Sometimes you'll be able to detect those things by sight alone, depending upon how the symbols are visualized on the screen, and how zoomed in you are, how close you are to those points. So if you took a space shuttle approach, it would be hard to detect the positional differences at the scale of cities around Seattle. But if you zoomed in to where you're looking at the road network of Seattle, it would be relatively easy to detect if those things were wrong, if they were in the wrong location, especially if you're comparing it to other data that you already have that you know are accurate.